Okay, so we'll see how this goes. It's a little weird talking when nobody's here, but here goes. So earlier we talked about the difference between simple interest and compound interest. So just to go over some of these formulas here. For simple interest, the interest is proportional to the time period, the interest rate per year, and the principal and present value. So this is where we get the interest I equals NRP. Future value then is the principal plus the interest, P plus I. And you put these two together, add them, and factor out the P, you get F equals 1 plus NR times P. Now for compound interest, this is slightly different, and somebody pointed this out after class actually, that the N for the simple interest here is not quite the same N as for compound. The N here for simple interest, just think of it as the number of years, whereas for compound interest, it's really going to be the number of interest periods, so the number of times over which it's going to be compounded. So for compound interest, we're going to have a new variable m, which is the number of times that the interest is going to be compounded per year. N then is the number of interest periods, which is going to be the number of years times m. So for instance, if you have 3 years and you're compounding monthly, this is 3 times 12, it's 36. I then is the interest rate per period. So what we're doing is taking the interest rate per year and we're chopping it up into a bunch of pieces, chopping it up into m pieces, so divide by m, and that gives you the interest rate for each of those pieces, and that's I. Then the future value, F, you get from the original principal, and you multiply that principal by 1 plus I n times, so you end up multiplying it by 1 plus I to the n power. So the example we did from class was $2,000 invested at 8% annual interest rate for 3 years, finding the future value. If you do simple interest, then the future value is 1.24 times 2,000, or 2,480. If you do compound interest once per year, so you're only compounding once a year, then after 3 years, you get 2,000 times 1.08 cubed. So times 1.08 times 1.08 times 1.08, or $2,519.42. From a lot of these are going to be rounded. I'm always rounding to the nearest cent here. So notice this is more than with simple interest. You're always going to get more future value with compound interest than with simple interest. If you compound monthly, more frequently compounding, you're going to get a bigger future value. But notice it's not that much more. For this one, we have m equals 12, because there's 12 times that we're compounding per year, which means n is 36, 12 times 3. In the formula then, 1 plus the interest rate, now we're chopping up that 8% interest rate by 12, so 0.08 divided by 12 makes 0.06 repeating. But really, if you're doing it on the calculator, don't use these repeating decimals, because if you truncate them, you're going to lose some accuracy. So you really should just enter it in as 1 plus 0.08 over 12, in parentheses, raised to the power. So don't do, if you can avoid rounding until the very end, then that's going to give you a more accurate result. It's probably not going to be off by much, but you'll get a more accurate result. So we've got 1 plus 0.08 over 12 raised to the 36 power times 2,000. That gives us $2,540.47, only about $20 more, not a whole lot more. If you compound daily, take m to be 365, 365 times 3, so 1,000-something days, and you chop up the 8% into 365 equal pieces. You might think you make a lot more, but look, it's only about $2 more. So 1 plus 0.08 over 365 to the 365 times 3 only gives you about $2 more. In case you're interested, if you want to, it seems like this is getting closer and closer to a limit. If you do it continuously, what would be continuous compound interest, turns out no matter how frequently you compound it, you're never going to make more than $2,542.50. So that's the most that you could make no matter how fast you do it. So only another 7 cents from daily to continuous. Not that big a difference. Okay, going on to second page. Let's look again at this this formula, the f equals 1 plus I to the n times p. There's 4 unknowns here, so if you know any 3 of them, you should be able to find the 4th. If you have an equation with any number of variables, if you know all but one of the values of the variables, you should be able to solve the other one, because you get an equation just for that. So I'm going to go through some examples where we do this for all 4 of them. We just did it for f. That was just the last example. We were finding the future value given the other 3. So let's do one where we're finding p, present value. So an example of this kind of problem. Calculate the present value of $10,000 payable in 8 years at 2.4% compounded quarterly. So this is saying we want to have $10,000 in the future, 8 years from now, and the interest rate is going to be 2.4% stated rate, compounded quarterly. So F is 10,000. R is 2.4%, so 0.024. Quarterly means we're going to be doing it 4 times a year, so M is 4. And then the interest rate per period is R over M, so 2.4% divided by 4 is 0.6%, or 0.006. There are 32 interest periods, because if it's quarterly and there's 8 years, there's 4 times 8 is 32 interest periods. Okay, so those are the variables that were given. What's left over in the formula? Well, P. So that's what we're going to find. If you take this formula, F equals 1 plus I to the n P, then you can solve it for P by dividing by 1 plus I to the n. And this is the expression that you get, this F divided by 1 plus I to the n. So you can almost think of this factor on the bottom here as kind of taking the future value, and in a sense it's discounting it. That's actually a technical term. It's said to be the discount rate as you go backward in time. Just like the 1 plus I is a number bigger than 1 that makes it bigger. 1 over 1 plus I is a number smaller than 1 that makes it smaller. So P, the present value, is going to be the 10,000 divided by, let me put this back up here, there's I, divided by 1.006, all to the 32nd power. And if you punch that into a calculator, you get $8,257.80. Again, rounding to the nearest cent. So this is the amount of money you would have to have now if you put this amount in now and you left it at 8 years, 2.4% compounded quarterly. In 8 years, it would be $10,000. Okay, so that's finding present value. What about the interest rate? Let's say you're interested in a certain interest rate. So I need to talk a little bit about this distinction between... Okay, I'm back. I clicked on something and I guess it paused the video, so you probably didn't notice it, but I was gone for a couple minutes. Okay, so we need to talk about the difference between the nominal and effective interest rate, because it's an important difference here. So The nominal rate is the stated rate. So it's the rate that's just the stated rate that's given per year. That's not really the one that you're really interested in now. What you're really interested in is the effective rate. The effective rate is the actual rate. It's the rate that you're actually going to pay, or it's the rate that you're actually going to have as a return. So in this problem, find the nominal rate and the effective rate of interest at $50,000 is desired. So we want $50,000 in 10 years. And we have $30,000 currently. And we're going to be compounding it monthly. So we know how much money we have now. We know how much money we want to have in 10 years. What's the interest rate that we'd have to achieve that goal? Okay, so how can we figure this out? So we're going to start again with our f equals 1 plus I to the np, the 4 variables. We know f, we know p, we know n. 50,000 future value, 30,000 present value, and n, the number of interest periods, since it's compounded monthly, 10 years, 12 times 10 is 120. If you plug these three in here, you get 50,000 is 1 plus I to the 120 times 30,000. We want to solve for I. So first we'll divide through by 30,000, and this will give us, just a second. Okay, this gives us 5/3 equals 1 plus I to the 120. Okay, now this is a little bit trickier to solve than the ones that we've been doing so far, because we've got this exponent 120. So what we need to do to get rid of the exponent 120, we need to raise both sides to the 1/120th power. So if you remember about fractional exponents, if you want to get rid of the 120 power, you're taking the 120th root, just like you take the square root to get rid of a square, cube root to get rid of a cube. In terms of fractional exponents, that's raising it to the 1 over that power. So the 1/2 power is the square root, 1/3 power is cube root. So we're raising it to the 1 over 120 power. So we're literally taking the 120th root of 5/3, the number 5/3. And that's 1 plus I. If you subtract 1, then we find that I is 5/3 to the 1 over 120th minus 1. That ends up being, if you plug this into a calculator, so you have to go 5/3, you have to use the caret symbol, or it's sometimes a y to the x, so whatever the button is that is exponentiation, takes one number to another power. And then subtract 1, you should get roughly 0.004266. So a little over 4/10 of 1%. Now, you have to remember this is the interest rate per compounding period. This is not per year. This is per compounding period, which for us was months. So what that means is we have to take that monthly interest rate, multiply it by the number of months in a year, m is 12. That'll give us the nominal rate. So R is the nominal rate, is I times m, that's the 0.004266 times 12. That gives us a stated nominal rate to the nearest hundredth of a percent of 5.12%. So that's the stated rate that'll give us that return. Okay, I'm just about to the end of my 15 minutes, so I'm going to pause here and I'll pick up here on the next video, part 2, because I have a limit of 15 minutes.